Hey everyone, how's it going? Ooh, I've got my voice echoing here. All right, so welcome back to Computer Science 4300. We're into lecture 14 today. We are officially past the halfway point. I think the halfway point was the last lecture. How's it going? Some people saying hello, good afternoon out there in the chat. Okay, so let's just look at where we are in the course real quick. So we've got assignment 3, which is out right now. A lot of work to do in assignment 3, as I'm sure you've all figured out by now. And so you had a full 3 weeks to do assignment 3. So we've still got a ways to go there, about halfway through the assignment 3 due date. So if you haven't started assignment 3 yet, please get on assignment 3 because there's lots of stuff to do there. Then we'll have assignment 4, and again, you'll have more than 2 weeks to do assignment 4. This due date isn't completely finalized yet. I've moved around a couple of the lecture topics in the schedule here. I actually want to move up the description of the project and the examples of the project. So in the next class on Tuesday, that's when I'm going to spend that lecture talking about the project, so you can get a sort of a head start on the project. Now, one thing I did want to mention is that some people have sort of expressed concern that, the project is going to be a lot of work and it's kind of, you have to start it on your own pace and you're going to be doing assignments while you're doing your project. But the thing is, all the things that are in all of the assignments are going to be in the project as well. So while you're working on the assignment, technically you're also working on the project, okay? So you're not doing double the work, essentially. You are completely free to copy and paste any code that you have used from any assignment into your project. So that's not a problem whatsoever. I do not mind self-plagiarism in this course when it comes to, for example, if you were going to make a top-down type game for your project, you could just take your assignment 4 code and build on top of that. All right? Yeah, so someone asked in the chat, it's not realistic for us to have done anything with the project other than daydream the style of game, right? Yes. So we will have one preliminary thing due for the project. I'll explain that next time, but you're going to have to hand in a project proposal, which is just a 1-page sheet on D2L, and that's explaining what you want to have done or the type of game that you want to make for the project itself. And then what we'll do is I'll look over those and tell you whether or not the idea sounds good or it doesn't sound quite good enough, and whether it's going to be enough work or whether it's not going to be whether it's too much work. I've told some people in the class before that this really sounds like too much work. So how about you scale it back just a little bit, and then if you get all this stuff done, then you can add the other stuff that you were thinking of doing. And so someone asked, would this be similar to the documents we submitted for 4770? No, so it's not the documentation part of that course. So 4770 was the software engineering course. It's the team project course. In this one, you're just submitting an idea for a game. It's not like all the different classes and stuff like that and the UML. It's just, here's the game we want to make, and here is how it fits your description. So in one sense, it's like the project, like the type of game description you had, but definitely not a big software document. Okay, so that'll be explained on Tuesday. So please tune in on Tuesday because that'll be an important one. But before I do that, we have some cool stuff to show off. So let me just minimize this so I can get a bit of a darker background. So I'm going to show off the cool solutions from assignment 2 today. So the TA picked out their top 10, and please don't be offended if your assignment is not included in this. It was sort of an ad hoc. Someone's saying, let's play Among Us. You can see I have Among Us here on my desktop. Not right now, maybe sometime. But the TA, as they were going through, they just sort of made some notes about what some of the cooler assignment 2s were in terms of the bonus. So you could get 100% on assignment 2 and not be on this list. So it doesn't mean that your assignment wasn't good. It's just these are some of the really cool bonus weapons that were done in assignment 2. So if you see your assignment here while I'm presenting it, please just put your hand up and say, hey, that's my assignment, okay? So here we have the first one. This one, so the TA renamed the executables with what is going on in the game. And this one is called grenadelob.exe. So if you did the grenade lob, please speak up. So here we go. You can see this. Here I'm moving around. I'm just going to let a few enemies spawn first. So here when I right click, oh, sorry, I didn't mean to have that enabled. I'll turn off the alerts, my bad. So here, if I right click, it actually lobs a grenade toward the destination, and then the grenade explodes and fires shrapnel here. Oh, awesome. We have the people in the chat who made this. So this is really cool because it simulates a 3D effect, but in 2D by making the grenade sort of be larger and then smaller. And up here we've got a grenade counter as well. So if I launch the grenade, it goes up in the sky and it falls down. So that's really cool. I really like that one. And just a question to those: do the grenades do they refresh at some point, or am I just out of grenades for now? You get grenades every 10,000 points. Okay, so let me kill something. There we go. Yep, so I crossed over 30,000. I got another grenade, and now I'm going to use it there. That's really cool. Alrighty. So the next one is called It's High Noon, and I think I might need some sound for some of these. Let me turn the sound up. So I've only run a couple of these, so I'm not even sure what this one does. Let's see here. Let me get a few enemies on the screen. And so if I hold right click, oh, that's cool. Okay. So it auto locks on targets, I guess. This one seems to be bugging out a bit. Let me go back here. So it's high noon. I'm assuming that's a reference to McCree in Overwatch. Oh geez, I died there. So it's high noon. Yeah, that's cool. So it freezes everyone in place and sends out the attack at them. Oh, that's really neat. So did anyone in the chat do this one? I'm just curious how you implemented it. So you must have put something onto the entities so that they're not allowed to move anymore. That's really cool. Yeah, that's pretty well done. Awesome. This one is called No Escape. I'm not sure what this one does. I can't remember. Let me just get a couple of enemies. Oh, okay. I see this. I think this is a homing missile. Yeah, so you can see here we've got a homing missile, and these the bullets actually steer towards the enemies. And then the entities come back as bigger entities. Oh, that's cool. So here you can see that whenever something is hit by something, it comes back later as a bigger entity. That's really neat. So there must have been like a custom. Cool. Did you have a custom component to do this? Did you add a new component to the game? That's really cool. All right. This one is called No Kill Run Any %.exe. I don't know what that means, but let's get a few things on the screen here, and then I'll shoot. Okay, so these fire bouncing balls that bounce off the side, and then eventually they might impact. Awesome. That's cool. I like the gradient checkerboard effect as well. Yeah, I saw the flash component in the last one. That was really cool. This is a neat bonus weapon as well. Oh, it bounces off me too. Oh, that's cool. Oh, and the number keys play. So someone in the chat knows all about this one. He must know the people who made it. Oh man, that's like seizure-inducing. So the number keys change the background, and you can play passively by pressing left Alt. Okay, I'm not sure exactly what that means, but I'll go on to the next one for now. Oh, and they changed the mouse cursor too. That was pretty neat. This one is called Passive Shield. So you've got this shield sort of going around you, and if you right-click, it's oh, who's the League of Legends champion? The dragon. What's the dragon's name in League of Legends? That's what this reminds me of. Someone out there, Orion Sol. Yeah. So this is what that reminds me of. So this is his sort of passive shield, and then when you press right-click, it's a larger shield. That's really cool. Nice. This one is called postproductionfx.exe. So let's see what this does. Oh, cool. So there's like this trail that goes behind the things. I'm not seeing a special weapon in this one. I'm guessing that's just the special effects. Did anyone out there do this one? Can tell me what the special effect might be? Oh, the special weapon is ready. All right. Oh my god. Sorry. That must have been really loud. Okay. Okay. I gotta put in my headphones because that was probably coming through the mic as well. One sec. That's really cool though. Let me do that one once more. So I'll click here. Special weapon is ready. Neat. All right, that was pretty cool. I like the special effect. Did someone out there say that that was theirs? If so, how did you accomplish the trailing effect? This one is called relevantgame.exe. Oh, that's hilarious. So the super weapon is the imposter, it says, and so the super weapon comes back to kill me. Ha ha ha. So yeah, this is a reference to Among Us, I guess. That's really good. I like that. Completely different take. I've never had a super weapon bonus actually come back and kill me before, so that's a good one. Really well done. You got me. Right-click memes, middle mouse button screams. Okay. What the hell is this one going to be? So I'm going to click the middle mouse button. Oh, okay. Interesting. The right mouse button shoots out ferrets, apparently. Let me restart this. So we'll restart, we'll wait for something, and then we'll right-click. Nicely done. So there's a sound on this one, but it's a bit low. That's pretty cool. So it homes and tracks enemies as they're there, and it has a lifespan. And then let me get a few enemies out there so I can hit this middle mouse button and see the effect. Because that was a really cool effect. Oh, that's cool. So you've got part of the project done already. Nice. That's a really cool lighting effect, and you submitted this before we even did the lecture on this. Oh, so you used that. That's cool. You already used the lecture. You found that before I told you about it. That's really nice. That's awesome. That's a really cool visual effect. This next one is called Super Hexagon. I know what the game is. Let's see what the special weapon is. Let's spawn a few things on the screen here. Okay. So, Super Hexagon. Oh, that's cool. So it's the actual Super Hexagon special effect. That's really cool. And there's a special weapon cooldown in the bottom left that ticks down, and now we can shoot it again. Cool. That's really neat. And the last one is called Tether Shot. And I think when I ran this one has sound and music as well. Okay. So it also has this really cool screen shake effect. So as I'm shooting things, the screen shakes, and then the tether shot it tethers me to an enemy, and then I think when I right-click again, I swap positions with it. Is that what happens? So when I hold right-click, it slows down time. I let go, it tethers me to something, and then I can swap with it. So that's really cool. That's a lot of really neat special effects. So again, hold right-click held down, shoot it out, and then swap. Yeah, this is really cool. This is how you get full bonus mercs, right? Well, you probably don't even need this many. But this is a really, really cool effect. Yeah, so I posted a little bit of a meme on Discord about people going all out with the special effects, and this was one of them. So well done on that one. This was one of the cooler ones, I think. And like, how easy is this to do now with ECS, right? How hard would this be without ECS versus how easy it is with ECS? All right, cool. So those were the 10 that we had, and again, if yours isn't there, don't be too sad. The TA just picked out 10. I didn't get a chance to look at all of them. All right, so those were the coolest solutions from assignment 2. And now I want to get into the lecture for this course, which is on 2 topics. One is on pathfinding, and another is on steering behavior. And we'll see what these things are, and both of these will have to be on the project. So on the project, you will have to have some sort of pathfinding, and you will have to have some sort of steering behavior. So let's get into the PowerPoint. Cool. So I think we've actually covered everything that we need to know for assignment 4 already. I believe that that's true. So up until now, we've been covering topics that you need for assignment 4, and from here on, it's just extra stuff that you have to have in the project. So none of this stuff is needed for assignment 4. Okay, so pathfinding and steering behavior. What is pathfinding? Everyone can probably answer that already, but let me just mute my desktop audio. Or no, I want to have the desktop audio because I think I have some videos in this slide. So video game maps are often filled with obstacles with which NPCs will collide. Pathfinding is the method that we use to determine which path an NPC should take from its current location to a goal location. All pathfinding algorithms attempt to minimize some cost of the path. That cost that we're trying to minimize could be a number of different things. It could be total length of the path, so the distance traveled. Maybe it could be the fuel consumption if you're in some sort of driving game. It might be the damage taken if you're playing some sort of tower defense type game, or it could be any arbitrary function. So you have to have defined in your game a cost function for the paths, and then your pathfinding algorithm will try to minimize that. And for anyone who is also in 3200, there'll be a bit of overlap. About half of this lecture is overlap with 3200, but the other half will be related directly to video games. So there are different types of considerations that you have to make when you're talking about pathfinding for your game. It's not just one solution for everything. You could have a single agent or multi-agent game, right, where you might have to, maybe you're just guiding one agent around a level, or maybe you're guiding a bunch of NPCs around a level, and now you have to consider things like NPCs bumping into each other or not. You may have a single goal or a multi-goal. So for example, if you're just trying to solve a maze, maybe you have this single goal, or if you're trying to get an NPC toward the player, you just have the single goal of get to the player. But maybe you also have multiple goals in the level. For example, let's say your NPC is really low on health and you wanted to get to a health pack. And so there might be 10 different health packs in the level. So maybe you're trying to say, get me to the closest health pack. So you could have multiple goals as well. You could have static or pre-computed pathfinding. This is done in some games. Or you could have dynamic or online pathfinding. Static or pre-computed pathfinding is a bit less common, but if you have games in which, say, the player is the only thing that's moving, you might be able to pre-compute some type of pathfinding that you can just look up in a table or something like that when you actually go to do pathfinding in your game. Versus dynamic, you might have like moving objects and stuff, or moving obstacles that you have to get around. You also have to consider what type of movement directions that you want to be allowed in the game. So for example, can you just move up, down, left, or right? Can you move in all 8 directions? Or are there arbitrary angles and movement? Maybe you can jump or fly in 3D space, right? There's all sorts of different things that you have to consider here. So for a single agent, this would be an example of a single agent scenario where you just have one agent. Oh, excuse me, one second. So you just have one agent up here at some starting location, and you're trying to get to a goal location. In multi-agent, you may have a bunch of different agents that are trying to get to a goal, and maybe they collide with each other, right? And so your pathfinding may have to take that into account as well. Again, just some examples of the number of different movements you could do. If this was your game world and you could only move in 4 directions, then maybe your path ends up looking like this from the start to the goal. So you'd move down, you'd move over to the goal. If you have 8 directions, maybe you can move on diagonals like this, and so your resulting path may be a bit shorter. Or if you have arbitrary straight line movements, you could have any path to the goal, and so you're not as restricted. So here's an example that I have from StarCraft of multi-agent pathfinding and why it's so important. So let me see. This is an example, it's really blurry, of I want to move a bunch of my siege tanks around this wall. So what actually happens in the StarCraft Brood War pathfinding engine under the hood is that whenever you try and guide a bunch of units at the same time, it actually creates a single path and then has all of the units just try and go along that path. And so let me just play that again, and you can see what happens. So the game engine creates a single path, and then what happens is all of the units try and get to the next waypoint on that path. And what ends up happening is now you had this nicely tight group of siege tanks at the beginning, and they're all in this sort of straight line now. And so while they're going single file into a base, the enemy can just pick them off. And so ideally, if you're doing multi-agent pathfinding, you can keep the group structure of what you have. Now, really arbitrary multi-agent pathfinding is a bit out of the scope of this course, and there's no single best possible solution. So we won't be going into that in this course, but here's just another example. Let's say I've got a bunch of units, like these SCVs here, and I tell them to attack this building. And you can see what's happening is that all of these units are getting stuck on each other. If you were trying to surround this building as quickly as possible, you'd probably have one group go over here first and then come back in. And so you can see how important this is. It could mean easily the difference between a win or a loss in a video game, depending on how you've implemented the pathfinding. But now in StarCraft 2, there is a much, much better pathfinding engine. And so this is just showing the difference of how your pathfinding engine can make a huge difference in the game. So this is a group of Zerglings in StarCraft 2 all swarming together and really keeping that shape inside the pathfinding engine. So in StarCraft 2, it does this thing that's a bit like rubber banding, where it will actually group all the units on top of each other for a second or two and then split them out. And so when a group is moving together, they can move together better because they can sort of sit on top of each other for a little bit. And so the pathfinding engine sort of cheats a little bit with the unit clipping in order to make the pathfinding better. But you can see just how much smoother this is and how much nicer it is overall. Also, pathfinding in your game could have pretty disastrous effects if you don't take... let's say you have a 3D game. So this here is this Saints Row or Hitman? I think it might be Saints Row. Saints Row 3 or something like that. So this is an example of a 3D game using a 2D pathfinding engine and not quite getting it right. So let's have a look at what happens here. What's going on? is this really not... Oh, here we go. So obviously the game developers didn't think about this bridge being open when they did the pathfinding for the game, and so you get this really hilarious effect. All right. Also, we could have something like threat-aware pathfinding, and what threat-aware pathfinding is, so we have Skyrim here, so you know the clip is going to be funny. Let me turn up the desktop audio here, because there is audio. So what you'll see in this game here is that there's a trap, and the trap is like this spiked wall. And if someone walks on the pressure plate and triggers the trap, it'll just slam closed. And that works for the player, and it works for NPCs. And it's kind of funny because the NPCs literally watch other NPCs get decimated by this thing, and then the pathfinding doesn't take that into account. So, you know, that was a pretty easy puzzle. Yeah, but this is, it's a Bethesda game. You expect these sorts of things from Bethesda games. And honestly, if that kind of stuff didn't happen, you'd probably actually like the game a little bit less. Okay. So, so far we've been talking about, these grid-type structures and doing pathfinding in these grids. But of course, your game probably isn't going to be a grid-based game, right? You're going to have a more arbitrary sort of movement system in your game. And so I'll show you now what people do in order to do pathfinding in games that don't have these sort of grid-based structures. Okay, come on. Navigation meshes. So what if my game is not grid-based? Well, what they do, and this is, we go into this a bit more in the game AI course 4303, but whenever you do any sort of pathfinding algorithm, they pretty much all operate on a graph structure. And so you're going to need to translate your game into some sort of graph structure to enable these pathfinding algorithms. And usually, this graph, or a representation of that graph, is called a navigation mesh. And most pre-built game engines come with software to build and edit a level's navigation mesh. So if we were using a game engine here, what we would see is that as we're building the level, we can define this navigation mesh. And the navigation mesh does two really important things. First, it tells you which part of the level is actually traversable by your player. So for example here, the navigation mesh, you can cut out parts of it, and so here where you see this gray part, those are the traversable parts of the level, and anything else is actually not traversable in the level. So here you see the 3D view, and here you have the top-down view. And so for example, you may be able to annotate this such that these parts are walkable and these parts are not walkable. And then what will happen is the game engine will run its pathfinding with the centers of these squares in the navigation mesh as the nodes in the graph for searching your environment for the actual pathfinding. So the pathfinding is done at the navigation mesh level. Okay. So again, we may have to also annotate that graph with specific game mechanics. So for example, here we have an example of a game with tons of markup on it because we want the character to be able to move. For example, if I go off to the edge of this platform, we want the player to jump to this platform. And so Oftentimes what you have to do in games like this, where you have this sort of complex movement, is you have to annotate these edges and your navigation mesh to say that, okay, well, when the player walks here, I want them to be able to go over here, even though the spaces between those two pieces of the navigation mesh are not necessarily traversable. And so if you're wondering how this happens, like for example, how Spider-Man is allowed to attach itself to a wall in a Spider-Man game, then this is what they have to do. They literally have to go to every surface that they want to be walkable and either automatically generate a navigation mesh or manually generate a navigation mesh on that surface and say this is walkable, or he's crawling when he's on this, here's the animations that I want to play, etc. So that's just a sort of a sneak peek into what you would do if you were actually using a game engine and their pathfinding system. But of course, we're not, so let's talk about what we'll do in this course. So single agent pathfinding. Many graph search algorithms exist for finding shortest paths, each with their own properties. And so there's a bunch of common algorithms. You can use breadth first search if you want to be really basic. You could use Dijkstra. You could use the A-star search algorithm. But most video game pathfinding uses some variant of the A-star search algorithm. So the A-star search algorithm, we go into that in great detail in my Computer Science 3200 course, so the Intro to AI. Excuse me. So if you want a lot more details about the A-star search algorithm, you can type !playlist in the Twitch chat and go watch the lectures on 3200. But we'll go over the basics of the A-star search algorithm if you actually do want to implement it in this course. So A-star is it's A asterisk, but we call it A-star. It's the most well-known best first search algorithm. So there's a category of algorithms called best first search, and those use a heuristic. It's called heuristic search. And it evaluates nodes by using two values, G of n and an H of n. So G of n is the path cost so far to the current node n. We also have a heuristic function H of n. Okay, so I'll edit this line because that's a bit weird. And the heuristic function is a guess at how far a node has left to the goal. F of n is the estimate of the cheapest cost solution via node n to a goal. So what we're going to do at every time step is we're going to select a node from an open list with a minimum value of n or f of n, and then we're going to expand that node and add the children of that node back to the open list. So just to look at the actual pseudocode for A-star, we have a closed list and we have an open list. The open list is going to be implemented as a priority queue, and we're going to have a node which takes in the initial state of a problem, and the priority queue is going to be sorted based on the F value of a node, which is the G value plus the H value. And again, I know that this is, I'm just showing the pseudocode here, but if you want more details about A-star, you can just go to the other courses YouTube video and watch the entire hour-and-a-half lecture about the A-star search algorithm. And then the search algorithm just has one main loop that it keeps looping forever, and it has a termination condition. So if the open list at any point is empty, it means that we haven't found the goal, and so we return fail, so we have no path to the goal. Otherwise, if the open list still has nodes in it, we're going to take the minimum F value node from the open list, and we're going to call that our current node. If that node's state is the goal, then we have a solution, and we have a path to our from our node to the goal. Otherwise, if the state of the node is in the closed list, then we can continue. We don't have to continue this node. And what this does is the closed list represents states of the environment that we've already explored. And this state here, this line here, just ensures that we're not checking infinitely long paths where we go left, right, etc. Then we'll add the state of this node to the closed list, and then we generate, so we expand the node, we generate all the children of the node, and we add those children to the open list. And that's basically the A-star search algorithm. I'm not going to spend too much more time on it in this course. If you do want to implement A-star search, you're more than welcome to do that. But please go see the lecture from 3200 about it for more details. part of the A-star search algorithm is this idea of a heuristic function. And in order for A-star search to work properly, we need something called an admissible heuristic. An admissible heuristic never overestimates the distance to the goal. And so this can be seen as sort of an optimistic guess. And you know what? I'm going to skip these slides because you can just go, now that we have pre-recorded lectures, you can go to 3200 and you can look at this. So really quick, for people who aren't in 3200, I wanted to give a quick demo of these search algorithms. So on my website, if you go here, you can sort of play along with this. But this is a demo of my search tool on my website. So this is a video game grid-based map in which you can, all the directions are down here in the bottom right. So you can click and drag from a start to a goal, and it will show you the most optimal path, so the shortest distance path from one location to another location. And up here, if instead of showing the instant path, you click animated search, then what will happen is it will actually show you the states of the environment that are being expanded in the tree search in order to find this path. And so it's a really cool visualization tool. We can also change the algorithm. So if I want to try breadth first search, this is how breadth first search works, and I can speed it up a little bit here. This is how uniform cost search would work, right? And so if you're interested in search algorithms, this is a pretty cool tool for visualizing search algorithms. And that's the sort of stuff that we do in 3200. So if you're interested in this, I'm sure I'm giving some people in 3200 PTSD from assignment 2, but you got to show off the tools that you make, right? All right, so let's get back into there, but feel free to play around with that pathfinding demo. Okay, but something that we don't actually cover in that course is path following. So now that we have a path, how do we make our agent actually traverse that path in the game? Because we've done the pathfinding at the navigation mesh level, but how do we actually make it walk that path in the game? So the simplest way to do this is something called waypoints. And so each point along the path in your navigation mesh, or each node in your graph, you can consider as a waypoint that the character that you've done the pathfinding for has to follow. So the path to the next waypoint we've pretty much defined as always being clear. So our waypoints have to be visible to each other. That is one stipulation on the waypoint. So we can always walk from one waypoint to the next waypoint. And then as we go through the waypoints, we can stop when the NPC reaches the goal. So here's an example of a path that I had defined before. So let's say that I've translated our game into this navigation mesh, right? And so I've got this path in the navigation mesh, and now I have all of these waypoints which are just defined by the nodes or the cells in the navigation mesh. So what I can do is, in order to follow this path in the actual game, I'm going to go from the start to one waypoint, then I'm going to go from this waypoint to the next one, this one to the next one, this one to the next one, and I'll go like this, okay? So because of the way that I've done the pathfinding, I know that any two adjacent waypoints are always going to be traversable because they're right next to each other. So in that way, as long as I follow the waypoints, then I'm good. Now, I know that I've reached the next waypoint when I'm within some radius of that waypoint, okay? So if you are doing waypoint following, excuse me, if we are doing waypoint following, and actually we will have waypoint following in assignment 4, then what you have to do is, as you traverse toward the next waypoint, you're checking to see if you've actually gotten to that waypoint, and when you get to that waypoint, it's when you're within a certain distance of that waypoint. And then eventually, of course, you get to the goal. So that's how we take one of these paths in our abstract navigation mesh space, and then we actually translate those back to the game world and then follow these paths in the game world. Now, something that we could do is we could refine this path as well, because having all of these waypoints, there's a lot of waypoints here, and it may just be like, you may, if you're doing these waypoint following, if you have too many waypoints, it's going to look like really robotic movement. So what we could do is say only take every second waypoint, for example. So this is called So yeah, we could just go here and say, okay, go from here to here, then from here to here, from here to here, and we'd have the same sort of waypoint following system. But let me try an example of what's something called path refining. So in path refinement, what you want to do is take the path that you got in your navigation mesh and make it look a little bit more natural, right? Because we don't want these sort of up, down, left, right movements. We want our NPCs to sort of walk in a more natural way. So let me apply the following algorithm to this set of waypoints. So let me start at the beginning, and I'm going to keep going. I'm going to keep checking the next waypoints until I find one that is not visible from the start. Okay, so I'm at the start. I'm going to look toward the next waypoint. Is this waypoint right here, is this one visible to the start? Yes, it is. Is this one visible to the start? Yes. Is this one visible to the start? Yes. Is this one visible to the start? Kind of. We'll say no. Okay? So what I'm going to do here is I'm going to back up one, and then I'm going to say, well, if this is visible to the start node, then why don't I walk straight from the start node to this one? Why do I have to follow these waypoints? Right? If it's visible, if it's clear, there's no obstacles, then walk straight from the start to here. And then I'm going to do the same thing from this node all the way to the goal. And so in this path refinement, what I end up having is far fewer waypoints, and the path is a little bit more natural. Okay, so that's called path refinement. So after you've done your pathfinding, you can refine the path in your actual game world to be a little bit nicer. All right, now I want to talk about something called vector fields. So vector fields for pathfinding, so vector fields can be used for a lot of different things. They're used in mathematics, they're used in physics, but we're going to use them here for pathfinding. They're also called flow fields. They can be called influence maps or vector maps. So if you ever see any of these are what we're calling vector fields. So there are very efficient structures for pathfinding, especially in the case where we want to have many things pathfind to a single goal. So for example, if we're playing a game like Diablo, like an action RPG, or Path of Exile. So we have Path of Exile, we have Diablo, where typically every NPC on the map is going to be coming for the player, right? So let's say we have 100 different NPCs on the map, and we want them all to slowly move toward the player. Well, we don't want to have to run our pathfinding algorithm 100 different times, right? It would be really nice if what we could have is a single data structure that would be able to show us the shortest path from any point on the map to a single point on the map. So that's what we're going to use these vector fields for. So any case where multiple NPCs need to go to a single location, consider using vector fields for your pathfinding. So we must balance computation with how many NPCs, etc. So of course, if you have 2 or 3 NPCs, maybe you don't need to use this because vector fields do end up using a lot of memory. So if you want to trade memory for speed, vector fields are one way you can do it. So here's a demo of a vector field being used for pathfinding. So here, if you can see the mouse pointer on the screen, we've got 10,000 points that are all trying to pathfind toward the mouse pointer. And if we tried to do this by running the A-star search algorithm for every point to the mouse pointer, sure, maybe we could do A-star in like a millisecond, but even if it's a millisecond and we're running at, 16 milliseconds per frame for 60 frames a second, then we could only do 16 paths per frame. But here, it's doing 10,000 paths per frame, right? So how in the hell is it accomplishing this? Actually, there's 20,000 particles here. If you look up in the top corner, there's 20,000 particles. So how would we accomplish something like this? It seems too good to be true, right? So first, step 1, what we're going to do is create something that I've called a distance map. So let's say we want to go, let's say this right here is our goal. Okay, so this is our goal tile right here. And let's say one of our entities is currently right here. So this is our entity. The first thing we're going to do is we're going to create a distance map. So you can see here all of our different cells have different numbers on them. So the way that we create these numbers, those numbers represent the distance from that point in the map to the goal. So you're going to say, how the hell did you get that distance, right? It's not magic. Well, do we have to run pathfinding? No. What we can do is we can run a breadth-first search algorithm out from the goal location in all directions. So we're going to go in 4 directions. This really only works with 4 directions. You don't want to do it with 8 directions because of various properties that I won't get into. But we're going to go up, down, right, and left. And what we're going to do, of course, the distance from the goal to the goal is 0. But every time I go another depth in the breadth first search, I'm going to increase this number by 1. So from this location, I go up and I get a distance of 1. I go right, I get a distance of 1, down a distance of 1, left a distance of 1. This one's a little bit hidden. Now what I do, I continue on the breadth first search from each of these nodes for every legal action. So for example, let's say I'm up here at this node. I go left and I give it a value of 2, right? Because it's 1 more than 1. And that signifies that in order to get to this location using up, down, left, right movement, I would have had to go up and then left for a value of 2. I could go right, I could go up, etc. So I do this for all nodes, and whenever I see a new node that I haven't gotten to before, I give it a value of n plus 1, where n was the previous node's value. But of course, for example, when I'm generating the actions from this node, if it's not a legal move, for example, this is an obstacle, I don't give that cell a value. And if the cell already has a value, for example, this one already has a value of 2, I don't go backwards, right? I just go forwards. So what we have is now we have this thing called a distance map, where if we can store one grid cell for each cell in the map, we now know the distance from this cell back to the goal. Or sorry, back to the goal location. So we've computed the distance from the goal to every point on the map. And now what we can do is the following. We can take that distance map and we can compute directions. So all we have to do from each cell, let's say for example this cell over here, I'm just going to draw a vector from the current cell to the cell that's surrounding it with the lowest value. So here, for example, I'm at this cell with a value of 8. I look at all the neighboring cells. I see that this one is the lowest with the value of 7, and so I point toward that cell. Now, why do I do that? Well, it's because I want to travel in the direction where the distance to the goal is being minimized, right? So here, if I go to 7, then I'm going to point maybe between 6 and 5, right? Because I don't want to be able to, I can't go through this this wall, and so I'm pointing sort of diagonally down between the 6 and the 5. Now, this one uses diagonals. We don't have to use diagonals. We could just say, okay, 7 goes to 6, 6 goes to 5, 5 goes to 4, 4 goes to 3, okay? So that then, this is a vector field, because it is a field of vectors. So that's where it gets its name. It's literally a field or a data structure of vectors, and so this is called a vector field. And all we have to do, no matter where one of our points is on the map, so we could have 10,000, we could have 1,000,000 of these little particles, and if I want to know how to get to my goal location, all I do is go in the direction of the vector, and it's super easy. So here I would follow this vector, follow this vector, follow this vector, and then follow this one, and I haven't had to do any pathfinding whatsoever for that particle because I have this vector field. So let's just look at what this looks like here. So here's the distance map, right? So as I'm moving the mouse pointer around, it computes the distance map in real time, and also it computes the vector field from the distance map. See how that works? So that's what's actually happening under the hood in order to guide these particles. So that's pretty cool. We get really, really fast pathfinding. Now, these might not be like the 100% complete optimal paths, but they're pretty good and they work. And if you have 20,000 points that you're trying to guide around a map, then this is really the only way that you're going to be able to do that. So the last 4 slides that I showed are from this tutorial online, so please go check that out. Give them some love for their good visualization that I borrowed. Okay, now that we know what vector fields are, we can talk about influence maps. So influence maps borrow the idea of vector fields, but they can allow us to do more than just simple pathfinding. So influence maps typically incorporate other logic into them other than just the simple distance to goal metric. So influence maps are used when it's difficult to come up with an objective function for other algorithms. So for example, when we're doing our pathfinding, we may want to do things like avoid attacking enemies. Or we may want to have the shortest path, but we also want to avoid getting too close to walls or enemy bases, for example. And it's very difficult to incorporate this sort of logic into a single value that we want to minimize or maximize. But influence maps can help us do that. Okay, so I've spelled influence map incorrectly here, but whatever. So let's say we have a goal down here, which is in white for some reason, and we have a starting location up here. And we want to pathfind from the start to the goal. Okay, so we can do that again by doing the distance map. Okay, so we have the distance map, and let's say we want to just avoid an enemy. Well, we want to avoid the tile that the enemy is on, so we just make sure that that is not a legal action. And so the distance map we get, in order to go from the start to the goal, how would we go here? Maybe we'd go down. So we just follow in the direction of decreasing numbers. So we go down like this. We come here, and then we go down because we don't want to walk on top of the enemy, and then we'd go here like this, okay? So that's just that's the simplest possible example of an influence map where we just avoid a specific tile. But let's say, for example, we didn't want to go near the shore of this island or something. Let's say we're in a boat, and we want to avoid going near the shore if all possible. Maybe there's enemy turrets up here. Maybe there's something that we don't want to do. Or maybe we just don't want the pathfinding to get stuck on the geometry of that level. So what we can do is we can give those cells what's called an influence value. Okay? So let's say we give them a starting value of 10. And then what we do, as we fill out our distance map, we're just adding that value to the distance map. And so what we get is this negative influence because it's a higher number, so we want to avoid higher numbers. And then what will happen is that if this extended down here, we would only go down through here if absolutely necessary. And so now when we're taking our path, we're no longer going really close to this shoreline. Okay? Now, let's add back in the enemy. Let's say this enemy has some sort of attacking radius that we really care about. And so we don't want to go near the enemy because it's going to shoot us or something like that. So what we could do is give the values around the enemy, let's say this is his attack radius, some really large number. So what this 50 might represent is, hey, I would rather go 50 more units of direction to my goal rather than walk through this cell. Okay, so what we get here is now when we fill it out, we have this as the influence map, as the distance map because of our influence. And so what we would do is instead of going down here, which we did before, we would actually have to go up around here to avoid that enemy. So this doesn't, influence maps don't always work this well for pathfinding. I've sort of cherry-picked a couple of examples, but I just want to give you the idea of what an influence map can be used for rather than the exact math that it's used for. But in practice, influence maps often are used. For example, I want to avoid this type of enemy, and so when I'm pathfinding, this influence map is going to be sort of repelling me away from this enemy. Or similarly, it's going to be drawing me towards the goal. Okay. Now let's talk about steering behaviors. So steering behaviors are very closely related to pathfinding, but they are actually a method of path following. And on the project, you're going to have to implement some sort of steering behavior. But they are very, very simple, so don't worry, it's not going to be a lot of work. So steering can be seen as a framework for controlling autonomous agents such as robots, CGI in movies, NPCs in games. It's used all over the place. And steering adds more realism and fluidity to agent movement and can enhance the experience. And steering, in my opinion, is actually really fun to implement and play with parameters and see what effects can be produced. So at its core, what steering does, it's literally steering, like when you're steering a car. So it just smooths the movements of entities in games. So changing directions instantaneously in games or stopping on a dime can look really bad. So for example, who has seen a game before where the NPC walks in a straight line and then makes a turn like this, right? Or walks in a straight line and then makes a turn like this. Like nobody walks like that, right? So what you want to do, what steering is going to do for us is it's going to allow us to produce paths like this. So if we were in a car and we actually had to steer, right? That's what steering behaviors are going to do. They're going to steer us toward a goal rather than like go straight for a goal. And the way it's going to do that is that the steering, we're going to have a steering force that smoothly guides an entity towards a target or away from a target based on the logic that we want to implement. So that's what steering is. Okay, so let's get into a little bit of math. Need to take a drink. Okie doke. So, let's say we have an entity in our game. So this is our entity right here. This entity currently has a velocity, okay? So that it says speed, but that's supposed to be velocity. I fix it on the next slide for some reason. So it currently has this velocity, all right? So it's going in this direction with a given magnitude. Okay, so I just changed that to velocity. Now, let's say something happens where I'm currently heading in this direction, but I want to be going toward this particular target, okay? So my current direction is right here for whatever reason that may be, but I want to be going toward this target, right? So this is my desired direction. So that's the definition. That's my desired direction. So based on this direction, I'm going to make a vector, and that's going to be the desired vector. So this is my current velocity, and this is my desired velocity. So I want my velocity to be this, but my current velocity is this. So in our game right now, without steering, what you would do is you'd just say, okay, I'm going to switch my current velocity to my desired velocity. Easy. But that's going to create this really jerky movement, right? In the game, you'll see it sort of stuttering like this. And we don't want that. We want smooth steering. So steering is all about how we get from our current velocity to our desired velocity in a smooth way. Okay, so let's calculate this desired velocity, keeping the same speed or the magnitude of our current velocity. All right, so our velocity right here is this xy vector. The length of that vector is our speed. Remember, the length of the velocity is our speed. So we want to compute, we have a direction, we have a target position, we have our current position, and we want to compute the desired velocity, which is the vector pointing toward the target, which has the same magnitude or the same speed as our current velocity. So, desired, this vector, that like this dashed vector, desired, is going to be target minus position. So my current position is here, my target position is here. And remember, to get the velocity from a point to another point, that is the target minus the source. Then I'm going to normalize the desired velocity, right? And we've looked at this before. So normalizing it converts it to length 1 by dividing each of the x and y by the length of the vector. And then we are going to change the desired length by multiplying it by the length of the velocity. Okay, so see how we do that? We get the entire vector, the entire dashed line, and then we normalize that vector to get a unit vector, and then we multiply the unit vector, which has length 1, by the length of the original velocity vector. And so that is our new desired vector. Okay, so now we have our current velocity and we have our desired velocity. And what we're going to do is create a steering force. Okay, so this steering force vector is the desired velocity minus the current velocity. So desired minus vel is steering. So here we are at the position of desired. So this up here, sorry, we're at the position of our current velocity. Here we would be at the position of our desired velocity. So in order to get the vector pointing from velocity to desired, we take desired minus velocity. Okay. Now, what we're going to do is we're going to follow the steering force, but we're going to scale that force by some scalar value. And so here, for example, I'm going to say, if my steering force was 0, then I would keep on my current trajectory and I would do no steering at all. If my steering scalar value was 1, then I would immediately switch all the way to the desired velocity. But I'm going to choose some value in between 0 and 1. Let's say right here it's like what, 0.3? And so what it's doing is it's multiplying the steering vector by 0.3, and then this black vector here is going to be my actual velocity on the next frame. And so typically what you'll do if you're running at like 60 frames a second, then your steering force will be quite low. It'll be like 0.1 or less. And what you'll see is that you'll find yourself steering very smoothly toward a target. So here what we have now is we have our current velocity over here. We have our desired velocity. We have calculated the dashed green steering vector. Then we scale that steering vector by a scalar value that we choose to be essentially how smooth or what is the delay in our steering. And that vector is the force then that guides us. So on our next frame, we're going to actually change our current velocity to the actual velocity that we want to have. So here's the math for that. Really easy. Here's how we calculate the actual vector up here. So I say actual vector because it's the one labeled actual, the black one. And this is called the steered velocity. So we have our current velocity, we steer it, and now we have our steered velocity that I'm calling actual. So we choose a scale between 0 and 1, okay? And that's some pleasing value in your game. So you create a variable for that, you implement the steering, and then you tweak that value based on what you want. Then your steering vector is just desired minus velocity. And then your steering is going to be steering times scale, right? This is your steering force. And then your actual vector is just velocity plus steering. And so now that we've set up these vec2 objects, all of this becomes really, really easy for us to do. So again, here's the steering math. Here's how you would do it in pseudocode. So you have desired equals target minus position, right? So again, desired is this really long, at this point, target minus pos gives us the dashed red vector here. Then we divide desired by its length in order to normalize it to get the unit red vector. Then we multiply desired by the length of the blue velocity vector in order to scale the red vector to the same length. Then our steering vector, which is initially the dashed green line, is going to equal desired minus velocity. Then we're going to scale the steering vector by multiplying it by the scale value that we've chosen. Okay? And then the actual vector is going to be velocity plus steering. And that's how it works. That's it. That's steering. So if you want to smoothly steer towards something, that's the math that you need to know. Okay. So there are multiple types of steering. The one that we just covered is called seek. Okay? So seeking sets our desired velocity to point directly at the target. And so this is important. So seeking behavior is I want to move directly at the position of the target where it is right now. Now, if you think about that, if the target is moving, maybe that's not the best possible thing we could do to get to the target. What we could do is something called the pursue behavior. And so the pursue behavior within steering is instead of steering directly toward the target, we're going to steer toward where the target is moving. So we'll calculate the target's velocity, we'll add that vector to the target, and then we'll pursue toward where the target is. So that's another type of steering that may get us to the target faster. Also, we could have a fleeing behavior. So maybe the thing that we're trying to steer, to implement steering for, maybe instead of wanting to go toward that target, we want to go away from that target. Maybe it's really dangerous or something like that. Or it's an enemy and we've run out of bullets or something. So we want to steer away from that target. So instead of just like immediately turning 180 degrees and running away, we can implement steering to gradually steer away from something. And the way we would do that is just by setting the desired vector, we multiply its x and y components by -1, and then we have the vector which points in the opposite direction from the target. And so we can implement fleeing behavior for free just by modifying the desired vector. All right. The one thing that we have to be very careful of, though, is something called arriving behavior. So let's say we're doing pathfinding using steering, and as we're getting toward the goal, which is a static goal, we're going to have really weird effects. So one issue with steering is that close to the target, the entity will oscillate. And what that means is that over here, let's say we have this target right here, okay? So if I have a target here, if I go the same speed the whole way, then I may steer past it one frame, and then go past it another frame, and then go past it another frame, and go past it another frame, where I'm just oscillating around the target, and I'm never actually really arriving at the target. So we're going to talk about this arrival behavior. And so one possible solution is that we're going to scale the speed linearly as it approaches the target within some distance. So what that means, for example here, maybe I have a fixed speed, or a fixed speed per frame between each of these updates out here, right? So I'm going the same distance. But then, once I get within some radius of my target, what I'm going to do is just scale the speed with the distance remaining. And so what's going to happen is, just like if you're parking a car, right? So let's say you're going 60 kilometers an hour, right? And you're trying to get to your parking spot in a parking lot. You don't go 60 the whole way and then just stop on the parking spot, right? You go 60, and then as you get closer, maybe you're arriving toward the parking lot, you go slower and slower, and when you're really getting right to the parking spot, you really slow down to like 1 or 2 or something like that. So that's what this does. You can scale the speed as you approach the target so that you slow down and slow down and slow down, okay? And the thing is that there's no best value here. There's no best algorithm. You just have to try it. And with all forms of steering, the correct behavior is the one that your game designer thinks is the best looking for the game, okay? So there's no absolute best behavior here. You just have to try it out, and you have to parameter tune and like your scaling values and your distance threshold and all that kind of stuff in order to come up with the steering behavior and the arrival behavior that you really want for your game. Now, of course, you don't always want arrival behavior, because let's say your steering is for a homing missile, right? You don't want to slow down as you approach the target. You want to crash right into that guy. And so you don't always want arrival behavior, but sometimes you do, right? So this is completely up to you as the game designer. And then as the game programmer, which is what this course is about, you have to implement it somehow. Okay, so I'm almost out of time here, but what I just wanted to show real quick was this open steer. So there's lots of cool examples on this website. Let's go to programming real quick. So it's on the, if people want to, lots of code here if you want to check that out, and lots of demos. I don't think there's I would have to download it, and I'm not going to do that now, but it goes through all of the different types of steering. So for example, there's seek and flee, pursue and evade, wander, arrival, obstacle avoidance, containment, wall following, path following. Let me show you one thing that we didn't talk about. So you could actually do obstacle avoidance in here. Let me bring this back up. By just saying, if you can calculate, let me get the pen. So let's say I want to, my desired behavior, my desired target is over here somewhere. Actually, I have a desired target. This is my target. But let's say that there's an enemy or an obstacle in the way. So the cool thing about steering is that you can have multiple steering forces. So let's say this is some lava or something in the middle of the map, and I want to steer away from that. What I could do is I could calculate this vector toward the lava, and then calculate the orthogonal vector to that, and then use this as a steering force in order to navigate away from that, but also navigate toward my target. So I can have multiple steering forces acting at the same time, and when combined, they can actually do some obstacle avoidance for me. And so steering is super, super powerful. And when you go to implement that on your project, please have a look at this website because it has a lot of cool examples. And there's like crowd path following, leader following, queuing, flocking, all sorts of different cool stuff here on this this reference. Okay, so tune in next time because I'm going to be talking about the project. So the project is super important. As always, it is worth half of the course, okay? So I'm going to be doing that on Tuesday on the next lecture, so please tune in then. And then after the project, we will be just continuing on with all the game programming topics that you will need for the project. So cool stuff like how to build a level editor, because your project will have to have a level editor as well. So whoever did 4770, you're going to be re-implementing what you did for 4770. We're going to talk about shaders and game loops and dragging and dropping and all sorts of cool stuff like that. So that's it for this lecture. Thanks everyone for tuning in. And I'll see you on Tuesday.